Okay, we have done for two scenario just now. So we're going to look at a new section. A new section is we're going to look at fully developed laminar flow in a pipe. So we start looking at what happens if we have a fully developed laminar flow. So again, laminar flow, the word laminar means that you need to call back the magic number 2300. The Reynolds number must less than 2300. Then you will get a laminar flow scenario. Okay, so in this section, when we mention about fully developed laminar flow, the flow is asymmetric. So the flow is asymmetric. What does it mean? It means that it is symmetrical in all directions. Asymmetric, it means that it is a round body and it is symmetrical for both sides. No matter how you flip it, we have an asymmetric scenario. So we will work on the cylindrical coordinate. We use cylindrical coordinate. Yeah. Previously we used Cartesian. Now because we are using pipe, so it's very convenient to use cylindrical coordinates. All right. So as what you see on the screen here or on your screen, you will see that there's two diagrams there. Let's start with the one on the left, which is this one. So you're having a pipe and you have a center point at the center. So the radius is capital R of the pipe. And let's say we are interested to look at very small changes in a small element inside the pipe here, which is the R element. Okay, so if you cut this pipe into half, the top layer, let's say you have a control volume, so you have a control volume here. So you cut the pipe into half, so you have a top plate again, bottom plate again, and then you have a small dr here. So you cut this one, let's say you cut into half, you'll see the dr over here. Dr is this one, like what you see, dr, and then the dx is the length of the pipe, the x over here. All right, same with this one, same is the top of this one. Yeah, so we have two sample here, one is at the below, one is at the top. But what is important is you look at the axis. Now the axis is at the center of the pipe, and is starting with the center. We measure up is R. So if you have a positive R value, means you are moving from the center to the top plate here. If you have a negative R, means you start moving down to the bottom plate. So be careful on the direction. So the axis is at the middle of the pipe with the R and X. Positive R means you're moving up. Negative R means you're moving down. And the size of the element we're looking at is dr and dx. Okay. So a few definition for the notation that we use. Dx is the length of our element. Dr is our thickness of our element or our control volume. So dx, dr. So for fully developed equation, we will recall what we learned in momentum equation in chapter 2. So we need to use momentum equation for control volume. This is our control volume. Then we will recall back what is momentum equation. So the S, the X component, for fully developed, the surface force in X direction, which is here, will be 0. There's no force at the middle here. Okay. So the first equation for fully developed laminar flow in a pipe, your surface force in the X will be 0. Right, will be 0 here because it's a steady developed flow. So surface force equals 0 in X direction. Then the next one will be, we will call back all the sum of the force for the element. So we take this element at the bottom there, we put in a bigger cube here. And like previously, we were looking at x direction only, or the force in x direction only. So from the left, you have a pressure times the area. You get force from on the left faces. Pressure times area. So how to get area is 2 pi r times the r. 2 pi r is the circumference of the cube here, and then times the r, you get the area at the sides. We are at a pipe, so you'll be using 2 pi r dr. Then same with the right hand side. Be careful on the arrow. Pressure always acting to the surface. So the arrow is always pointing in to the surface. Right hand side also same, but with the differential pressure here, plus dp over dx dx. So we already explained about this partial differentials equation in chapter 2. So if you're not sure, recap in the chapter 2 video. Go and listen it again. How we have a positive here, positive sign here. And then in x direction, we also have the shear force. So how to convert the shear stress into a force? You take stress times area, we get force. We see this example in the example in tutorial question just now. When we have a shear stress times area, we get force. So again, the area also 2 pi r dx. You will get force at the top, and at the bottom you will get this term plus partial differentials of your shear stress dr and r plus dr distance. So these four are the forces component. You sum up because all these will be in equilibrium. So this one plus this one plus this one plus this one will equal 0. The concept is to convert the pressure and shear stress into forces in x direction only. We only consider x direction only. All the force you add up becomes 0. Okay, so we have all this equation. So force on the left hand side, on the left faces here is P 2 pi r dr. On the right hand side is this one, negative. You have a negative sign because it's opposite the axis direction. All right. So all the direction to the right is positive. So this direction is opposite the normal x direction. So we get a negative sign there. So be careful on this notation. All right. When you convert information from diagram, be careful when you develop the equation. We have a negative sign here. Just take note, because it's against x-axis. Same with the top and bottom. So for inner cylindrical, you have this one. Inner cylindrical means on very near to the center of the pipe there. So you use the I for inner forces, this one, this component. So again, you have a negative sign because it's against the x-axis, right? Because the x-axis is positive to the right, the arrow is to the left, so we get a negative sign here. And shear force at the outer cylindrical, which is near to the wall here, so you'll get this equation, right? You add all these four equations here together, you'll get a very lengthy, very long equation. Is 1, 2, I think I missed out one. I missed out one more equation because we have four. We have four equations, yeah. Face left, face right, inner and outer surface. So DFL, DFR, DFI, and DFO. These four you add together, it becomes 0. So again, in my slides, there is a missing equation over here. you understand why I say we are missing one equation? Do you understand?
Yes.
Why? What is missing in this equation? Which equation is missing?
CV.
CV?
Sorry. DR.
What is dr? You understand what I'm asking or not? Do you understand my question?
Again, sir.
Look at this equation that you see on the screen here. There's one equation missing here. How many forces that you see in this equation? How many forces?
Three.
So on the control surface or control volume itself, how many forces you have?
3.
You have 3 forces.
Yeah.
You are seeing 3 forces just now. I explained about the force on the left, the force on the right, the force on the inner surface, the force at the outer cylinder. You are seeing 3 equations. So how many equations you seeing?
Two equation.
Total, how many equations you have?
4.
This equation is this one. This side. This equation is this side. This equation is this side. This equation is this side. So how many equations you have?
4.
4. So my question is, you are seeing 3 equations. So which equation is missing? Amir, next question is for you. Stand by.
The P2S DR.
Okay, I label for you force 1, force 2, force 3, force 4. Okay, force 1, force 2, force 3, force 4. Which force is missing in my slides here? In this equation, which force?
Force 1.
Force 1 is missing.
Yeah.
Okay. All right. So if you sum up all the force, at the end you arrive at these 3 equations. Yeah. If you sum these 4 together, F1 plus F2 plus F3 plus F4 will be 0. You sum up, you get 1, 2, 3. Okay, because all these are you sum all these equations together, you simplify, some you can cancel, some you can take out. At the end, you arrive at these 3 components. All right, then you divide this equation with 2 pi r dr dx. All right, you divide this one, you take out the 2 pi r dr dx in this equation. Then you solve for what is del p over del x. You will get dp over dx will be rho shear stress divided by r plus d shear stress divided by dr. Okay. Amir, you
Sir,
understand? Yeah.
sir,
Yeah.
for this equation, is there
Yeah.
if one is not missing, right?
Again. Again,
Uh,
your question.
if one is not missing, right? Because like oh, when we, for F1 is P2 pi R D R, right?
Yeah.
Uh, so for F3, for F2 it's
Mm.
when we multiply the 2 pi R D R by the inside uh, the quotes
Mm-hmm.
inside the brackets,
Mm-hmm.
it will this one is supposed to be negative, right? All of it.
Yeah. Correct. I
So
mean,
so that means
yeah.
uh,
Let me go a bit slow. I understand what you're trying to ask. Let me redo the mathematics for you guys. Then you will see what it might help you to clear your doubt. Okay. How to arrive at this equation? F1 plus F2 plus F3 plus F4 equal 0. So let's say this is force 1, this is force 2, this is force 3, this is force 4. All right, I write the first one here. P 2 pi R dr is your first force, which is positive. Then I continue with second force, which is negative. So negative P 2 pi R dr negative dp dx dx 2 pi r dr. This is the second force.
yeah, this is what I meant. Yeah.
Then continue with 3. Number 3 is negative also, going to the left. Negative shear stress Rx 2 pi R dx. Apologize for my writing using my mouse. And positive plus 4, you have shear Rx. There's a very lengthy equation over here. So 2 pi. Okay, let me do it a bit slow for the third one. It's a bit lengthy, equation number 4. Okay, let me rewrite the equation number 4. So you have shear plus d shear divided by dr. dr is a quadratic equation. 2 pi r plus 2 pi dr times dx. So it's a very lengthy equation. Yeah, you expand this whole thing, right? So you put this whole thing over here. Yeah, you put this whole thing over here. Equal 0. After that, you simplify the whole thing. How you simplify? You just cancel out all the repeated known. So P 2 pi r dx 2 uh, 2 pi dr again what is there's one more. Where is the no, there's no dx here. 2 pi dr, this is dr. All right, so we can cancel this one and this one. R, correct. 2 pi r dr. Yeah. So we can cancel the first one and then you keep cancelling. You arrive at this equation. Amir, you clear?
Yes, sir.
Cool, you understand how you arrive at this equation?
Actually,
Still
sir,
really confused.
actually, sir, this is what I meant, because at first I thought this equation is wrong and there is a missing force. Then I found this is the last normalization for this equation.
So basically, you just sum up all the force.
Yeah.
Then you will get,
Yeah, it's a quite long calculation,
yeah,
but this is the last one here.
yeah. This is the last steps you arrive. After you cancel all the each other lah, there's a repeated term there. One is positive, one negative. You cancel, then you arrive at this one.
Yeah, okay.
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 Cool, you understand?
Yeah, no, I understand.
So you just sum up all these four forces, then you write in a very long equation. Plus equation 1 plus equation 2 plus equation 3 plus equation 4. Then you expand the fourth one. Then you start cancelling. At the end, you'll get this equation. Right? Then after that, you simplify. You divide all these terms. Take out this term. Divide. Then you rearrange. You'll get dp over dx equal to shear divided by r plus d shear over dr. You just rewrite the mathematics model. And you can rewrite this one in this term. dp over dx equal to 1 over r dr shear divided by dr. Okay, this is just a mathematics rewrite the equation over here. Then after that, right? Then after that, you continue with the calculation. There's one scenario or one criteria is that you can only solve this equation when this whole equation equal to a constant, right? When you can only solve this equation when this whole thing equal to a constant value. So when it become a constant value, let's say 1, this constant value is 1, then you can rearrange this equation to this term. You move your r to the left. So you get r dp over dx equal to dr stress divided by dr. And this is a side note. This is a side note. So from this equation, you can see that the pressure will drop if you increase the pipe length. Okay. How do you read this statement? You look at this mathematics model, dp over dx. So if you increase your x, your p, you're going to drop. Yeah. So this is how you read this equation. Then we start to develop this equation by integration. So we just integrate this equation integrate with r. So this one, if you integrate with r, you get r squared divided by 2 plus a constant value. And this one, you integrate with r, you get r for this term. Then because you cancel just now, you cancel the r in this equation. Because r is constant, you cancel this one. And then you differentiate with r again, you get r2. Sorry, not that. You integrate straight away with the r. You'll get this term. Then you solve for the constant value. This slide is more about mathematics steps. So you keep integrating. Then you arrive at C1 and C2 constant value. You need to find how do you solve this C1 and C2 by using condition, boundary condition. So at u equals 0, because at the pipe there, when your r equal to r, which is near to the wall, your velocity at here will be 0. Then from there you can get your C1 equals 0. So velocity must be finite in r equals 0, means at the center velocity must be, there must be a value there. So your C1 will be 0. And then you rearrange the equation. Yeah, you rearrange the equation. Because ln 0 is a infinity value. So you don't have a value here. Yeah. Let's press calculator. Ln 0 equal to what? Ln 0. So ln 0 is an infinity value. So we can take out this one. Yeah? So at the end, this slide is just all on mathematics. Yeah? You can try to study it to get the constant value, and then you substitute back to the velocity profile equation. At the end, you'll get the velocity profile for pipe. So important for today, second session of the lecture will be these three equations. So u equal to this one, u equal to this one, u equal to this one. So you have three format of the velocity profile for pipe, and these three equation is for laminar flow. Okay, and the derivation steps already covered in the slides. Don't worry, in exam I won't ask you on the derivation steps. In exam, what is important is that you're able to identify or call back what is the equation for particular scenario. For example, if you are giving a scenario where you need to use a fully developed laminar flow for pipe, and the question asks you for velocity profile, straight away flip to these slides and use either these three. You can use the first one, second one, or third one, depending on the parameter that you have in the question. Clear?
Okay.
Yeah. So important is this slide. Important is this velocity profile. You'll get there are three formats there. You can either use the first one, or the second one, or the third one. It depends on the scenario that you have. These three actually is the same format, only the rearrange of mathematics model. Okay, the derivation steps, you just read through the slides and try to understand how do we get it. The step actually start from the force itself, right? Just recap. Start from the force itself, sum up all the force equals 0. There are 4 forces on the control volume itself. Add these 4 forces, these 4 arrow forces, become 0. Simplify the equation by taking out all the same factor. In this case, 2 pi r dl dx, you take out, divide, rearrange, rewrite in a new format, dp dx. After that, you integrate. Right? After that, you use this equation, you integrate. After you integrate, you'll get the constant value. You'll get constant value. After constant value, how you find the constant value by using boundary condition. So boundary condition, there are 2 boundary conditions. One is u equals 0 at the wall, and the velocity at the center is maximum when you are at the center, or there's a finite velocity. So you'll get your C1 equals 0, and then you continue with the substitution of the value. You'll get what is your C2, right? So R equal to R U2, you get what is C2. You substitute back to the equation just now. You have C1 and C2 here. That's why you get U equal to R something, C1 0, C2 is the one that you find. So you get a complete one. So from there, you get your first velocity profile equation with the small r and capital R in the term. Then the rest you just rewrite the equation, you factor out the same dp dx and 1/4 mu, and then you only have r squared minus r capital R, or you can rewrite in the ratio of r divided by r. There are three formats. Okay, so remember you have three format for velocity profile for laminar flow in a pipe. And this laminar flow is happen at a fully developed scenario. Okay, fully developed scenario of the pipe. So again, recall when you mention about fully developed, there's one particular slides that we always begin with in the beginning of this chapter with this equation, L over D equal to 0.06 Reynolds number. So you need your flow need to flow at a certain length to get fully developed scenario. So the ratio is L over D 0.06 Reynolds number. The scenario that we look at today is at fully developed region, which is you need to travel at a certain length to develop to reach a fully developed velocity profile. Okay, so just to summarize, what is important for second session is the velocity profile for a pipe, the three equations just now. Okay, just to summarize for today. I think it's enough. I don't want to go further because we have a few more equations. It's enough for second session with three more equations. All right, so with this, I end the recording.